At 8:40 in the morning, a blizzard warning was issued along Interstate 80 in Wyoming. Winds over 50 miles per hour. Visibility collapsing below a quarter mile. Heavy snow swallowing roads that should have been entering late spring, not returning to deep winter. But only a few hours later, nearly 2,000 miles away, meteorologists in Boston were warning that temperatures were approaching the upper edge of what modern climate records consider statistically possible for May. Not unusual. Not rare. Statistically extreme. The kind of atmospheric anomaly that only appears at the outer edge of a distribution curve built from nearly half a century of operational weather observations. And both events, the blizzard and the heat dome, were unfolding on the exact same day, driven by the exact same planetary-scale wave pattern stretching across North America. That is the detail almost nobody fully understands yet. This was not random weather. This was not coincidence. The atmosphere itself entered a configuration climate scientists have spent years warning could become more frequent during the 21st century. And tonight, while millions of people sleep beneath calm skies believing the worst has already passed, the data suggests this pattern may only be the beginning. Somewhere listening to this right now, someone is sitting under unseasonable heat that feels wrong for this time of year. Someone else is hearing tornado sirens in the distance. Someone else is watching wildfire smoke drift across the horizon. And somewhere high in the Rockies, snowplows are still clearing roads buried beneath heavy snow in the third week of May. This story is about all of them. It is about you too, because the atmosphere over your head is not isolated from the atmosphere anywhere else on Earth. The weather you experience tomorrow may already be connected to a wave forming over an ocean thousands of miles away tonight. And over the last several years, those waves have been behaving differently. Over the next few hours, we are going to trace the anatomy of one of the strangest atmospheric configurations ever observed in the modern era. We are going to explore how a single amplified Rosby wave generated simultaneous blizzards, heat domes, tornado outbreaks, flood risks, and extreme fire weather across the same continent at the same time. We are going to examine why climate researchers are becoming increasingly concerned about low phase speed resonance patterns developing inside the jet stream. We are going to look at how drought, warming oceans, shifting ENSO conditions, and declining soil moisture may now be pushing the atmosphere towards synchronized extremes more often than many climate models originally projected. And most importantly, we are going to confront the uncomfortable question quietly emerging inside the scientific literature right now. What if these events are no longer anomalies? What if this is the atmosphere adapting into a new operational state? Because buried inside technical forecast discussions this week was language meteorologists do not use lightly. Phrases like close to the maximum relative to climatology, 2 to 3 standard deviations above normal, major heat risk unusually early in the season. These are not headlines written for attention. These are cautious operational scientists attempting to describe patterns sitting near the edge of historical experience. And if you stay with me tonight, you will begin to understand why some atmospheric researchers now believe the models may still be underestimating how often these configurations can occur. But before we go deeper, take a moment to settle in and slow your breathing. If this channel helps you explore the universe, the Earth, and the hidden systems shaping our reality, consider leaving a like so this video can quietly reach the people who may need it most tonight. Somewhere out there, another person is lying awake trying to understand why the world feels increasingly unstable, increasingly synchronized, increasingly strange to. And maybe this journey through the atmosphere can help them feel a little less alone. Because what happened this week was not just a weather event. It was a glimpse into a much larger mechanism that has been building quietly for years beneath the surface of ordinary forecasts. Most people saw disconnected headlines. A blizzard in Wyoming. Dangerous heat in the Northeast. Tornadoes across Kansas. Fire danger in Texas. Flood watches in Missouri. Separate stories. Separate disasters. Separate local forecasts. But high above the continent, nearly 6 miles above the Earth's surface, the atmosphere was behaving as one interconnected system. A single planetary wave had amplified into a locked configuration powerful enough to bend entire regions into opposite extremes simultaneously. One side of the wave pulled Arctic air deep into the Rockies while the other side pumped subtropical heat northward into New England. The same structure producing snow on one edge was producing near-record heat on the other. And the deeper scientists looked into the historical data, the more unsettling the pattern became. Because this kind of simultaneous atmospheric amplification appears to be occurring more often than many climate simulations predicted. The implications extend far beyond unusual weather. They touch agriculture, water supply, insurance systems, electrical grids, transportation networks, food security, migration pressures, and the stability of infrastructures built around 20th century climate assumptions. Tonight's story begins with weather maps and forecast models. But before this journey ends, it may force us to confront a much larger possibility. The atmosphere above modern civilization may already be entering a state no human civilization has ever experienced before. Right now, above your house, above your city, above the clouds you would see if you stepped outside tonight, there is a river of air moving around the planet at more than 200 miles per hour. You cannot see it. You cannot hear it. But it controls almost everything about the weather below it. The storms, the droughts, the heat wave, the floods, the wildfire seasons. And this week, that invisible river did something so unusual that meteorologists across the United States began quietly using language usually reserved for once-in-a-generation atmospheric events. The strange part is not simply that the atmosphere became extreme. The strange part is that the atmosphere stopped moving normally, because weather becomes dangerous when systems intensify. But climate becomes unstable when those systems stop progressing forward. And that is exactly what happened. The atmosphere stalled into a configuration scientists call high-amplitude Rosby wave resonance, a state where planetary-scale waves inside the jet stream slow down, amplify, and lock entire regions beneath persistent extremes for days, or even weeks at a time. This is not science fiction. This is measurable atmospheric physics happening in real time above North America tonight. And if you understand this mechanism, you begin to realize why simultaneous disasters are becoming increasingly common across the modern world. The jet stream exists because Earth is unevenly heated. The equator receives far more solar energy than the poles, and the atmosphere constantly attempts to redistribute that imbalance through large-scale circulation. Warm air rises near the equator. Cold air sinks near the poles. Earth's rotation whisks those movements into powerful west-to-east wind bands high in the troposphere. But those winds do not travel in straight lines. They bend into enormous waves thousands of miles across. Those waves are called Rosby waves, named after meteorologist Carl Gustav Rosby, who first described their dynamics in the 20th century. Under ordinary conditions, Rosby waves move steadily eastward, carrying weather systems along with them. The storm arrives. Cooler air follows. Then another system replaces it. This constant progression is what keeps the atmosphere balanced. But sometimes the waves amplify. The ridges bulge farther north. The troughs plunge farther south. And most importantly, the entire pattern slows down. When that happens, weather stops behaving like temporary weather and begins behaving like a stationary atmospheric machine. The same regions remain trapped beneath the same conditions day after day. Heat accumulates. Soil dries out. Flood zones receive repeated rainfall. Wildfire corridors stay exposed to hot, dry winds. And because the pattern moves so slowly, each hazard begins reinforcing the next. That is what scientists were watching unfold this week. One side of the wave anchored brutally hot air over the eastern United States, while another side dragged cold Arctic origin air into the Rockies. Between those extremes, the atmosphere generated violent instability across the plains, where warm, moist Gulf air collided against descending cold air from the western trough. The result was simultaneous heat, snow, tornadoes, floods, and fire were all connected to the same atmospheric structure. And the more researchers analyzed these events, the more they realized the atmosphere may now be entering resonance states more frequently than earlier climate models predicted. Part of the reason involves the Arctic itself. The Arctic is warming nearly 4 times faster than the global average, reducing the temperature contrast between the poles and the equator. That contrast is one of the primary drivers of jet stream velocity. As the gradient weakens, sections of the jet stream may become slower, wobbler, and more prone to amplification. In simple terms, the atmosphere loses some of its momentum. The river begins meandering instead of flowing cleanly eastward. And when those meanders grow large enough, entire continents can become trapped beneath persistent circulation patterns. Scientists still debate the exact strength of this relationship, but observational data over recent decades increasingly suggests that slow-moving wave configurations are becoming more common during warm season transitions. The implications are enormous because modern civilization was built around relatively stable assumptions about seasonal behavior. Agriculture depends on predictable rainfall timing. Electrical grids depend on expected temperature ranges. Reservoir systems depend on snowpack cycles arriving and melting on schedule. Transportation networks depend on infrastructure designed for historical weather probabilities. But resonance events disrupt all those assumptions simultaneously. A single stalled wave can produce crop failure in one region while flooding another. It can create energy shortages during heat waves while wildfires threaten transmission lines elsewhere. It can destabilize insurance systems because multiple disasters happen at once instead of separately. And perhaps most unsettling of all, the atmosphere appears capable of producing these synchronized extremes without warning the public in language dramatic enough to match what is actually unfolding, because most people still experience weather locally. They think in terms of their city, their forecast, their storm. But the atmosphere does not think locally. The atmosphere behaves as one interconnected fluid system wrapping around the entire planet. And this week, that system revealed something extraordinary. It revealed that the boundaries between separate disasters may be far thinner than modern society ever realized. By Tuesday afternoon, parts of the northeastern United States were approaching temperatures that normally belong to the middle of July, not the early edge of summer. Cities from Washington to Boston climbed into the mid and upper 90 seconds, while the atmosphere above them behaved more like a desert heat dome than a springtime air. But the real danger was not simply the temperature itself. The real danger was timing. Human bodies adapt slowly to seasonal heat. Blood plasma volume changes. Sweat efficiency improves. Cardiovascular systems gradually adjust to prolonged warmth. But this process takes days or even weeks, and this heat arrived almost instantly. Just a few days earlier, much of the East Coast was sitting beneath cool spring air in the 60 seconds and low 70 seconds. Then the ridge amplified overhead, skies cleared, humidity mixed downward, and the lower atmosphere began compressing into intense surface heat. Meteorologists watching upper air observations noticed something deeply unusual at the 850 millibar level, roughly 5,000 feet above sea level. Temperatures there were reaching values nearly 3 standard deviations above climatological averages for the date. In atmospheric science, that matters because the 850 millibar layer acts like a preview of what the surface may soon experience. If extremely warm air exists there and vertical mixing becomes efficient, the heat descends toward the ground. That is exactly what happened. Dry air allowed solar radiation to rapidly warm the surface while descending air inside the ridge compressed and heated, even further ridge compressed and heated. The result was an atmosphere that behaved less like spring and more like a continental oven. But the most unsettling part was psychological. People could feel something was off. Trees were still transitioning into late spring foliage while sidewalks radiated midsummer heat. Schools remained open under temperatures more typical of July. Hospitals began preparing for early season heat stress cases. Power demand surged unexpectedly across urban corridors, not yet acclimated to sustained cooling needs. and quietly in forecast offices across the eastern United States, meteorologists began discussing whether this kind of early season anomaly would become increasingly common in the coming decades. Because heat itself is changing, not only in magnitude, but in behavior. The atmosphere is now capable of delivering highly amplified warmth earlier in the seasonal cycle, before ecosystems and infrastructure have fully adjusted. That creates a hidden vulnerability modern civilization was not designed around. And while millions sweated beneath the eastern ridge, another side of the same atmospheric wave was preparing something completely different over the center of the continent. While the northeast baked beneath record warmth, the central plains entered a completely different phase of the same atmospheric system. Across Kansas, Nebraska, and parts of Missouri, warm Gulf moisture surged northward beneath cold, dry air, spilling east from the Rockies. This collision zone created one of the most unstable atmospheric setups meteorologists can observe. The atmosphere essentially became stacked with conflicting layers of energy. Near the surface, hot humid air accelerated northward on strong southerly winds. Higher above, powerful west to east jet stream winds created intense wind shear, allowing thunderstorms to rotate as they developed. And inside those rotating storms, the atmosphere began producing some of the largest hail and strongest tornado signatures of the season. Forecasters monitoring radar velocity scans watched supercells rapidly organize into structures capable of giant hailstones, larger than baseballs and tornadoes, potentially reaching EF2 or EF3 intensity. The energy available to storms that afternoon was extreme. Mid-level lapse rates, the rate at which air cools with altitude, approached values more commonly associated with major severe weather outbreaks. This mattered because steep lapse rates create explosive vertical acceleration inside storms. Air parcels rise violently upward, carrying moisture and rotation into towering supercells capable of punching deep into the upper troposphere. But once again, the key point was not simply that severe weather occurred. Severe weather in the plains during May is normal. The disturbing part was simultaneity. The exact same Rosby wave producing dangerous heat in the eastern blizzard conditions in Wyoming was also generating violent convective instability across the center of the country. One atmospheric structure. Multiple disasters unfolding at once. And as evening approached, emergency managers across the region faced a difficult reality. The atmosphere was not producing isolated hazards anymore. It was producing synchronized extremes interacting across thousands of miles simultaneously. Tornado watches expanded eastward. Flash flood risks increased downstream, where repeated storms trained over saturated ground. Emergency alerts multiplied across multiple states at once. And somewhere high above those rotating storms, the planetary wave driving all of it remained nearly stationary, locked into place over the continent like a giant invisible engine refusing to move forward. At the exact moment millions of Americans were opening windows to escape abnormal heat in the east, another part of the country was disappearing beneath heavy mountain snow. Along Interstate 80 in southern Wyoming, visibility collapsed under violent winds and blowing snow as temperatures plunged back toward winter conditions. Snowplows struggled to keep roads open while gusts above 50 miles per hour pushed snow sideways across the highway. Drivers trapped along the snowy range corridor described conditions that felt more like January than late May. And yet this was not a separate storm system. This was the opposite face of the same atmospheric wave. Deep inside the western trough, cold Arctic origin air spilled southward into the Rockies while moist upslope flow forced air upward along mountain terrain. As the air rose, it cooled rapidly and condensed into heavy wet snow across elevations above 7,000 feet. Some mountain ranges received more than a foot of accumulation in less than a day. Meteorologists classify events like this as statistically unusual, but physically possible during spring transition month. But again, the true anomaly was not the snow itself. It was the combination. Blizzard warnings, tornado outbreaks, wildfire conditions, and near-record heat all occurring simultaneously across one continent under one locked wave pattern. And as climate researchers reviewed similar historical configurations, they noticed something unsettling. Many of the most damaging modern weather disasters were no longer isolated events. Increasingly, they were synchronized extremes connected through large-scale atmospheric resonance. One stalled wave could now create multiple national emergencies at once. Transportation disruptions in one region, crop damage in another, power grid strain somewhere else, insurance losses everywhere simultaneously. Civilization was built assuming regional disasters would remain regionally separated. But the atmosphere was beginning to test that assumption. Because once a planetary wave locks into place, every hazard beneath it begins reinforcing the next. Snowpack delays run off timing. Drought amplifies heat. Heat dries fuels. Dry fuels accelerate fire spread. Persistent storm tracks trigger flooding over already saturated ground. The system feeds itself. And for the first time in modern observational history, scientists were beginning to wonder whether these compound atmospheric behaviors were becoming part of a larger, new climate regime. Far south of the blizzard zone, another danger was unfolding beneath clear skies. Across Texas, New Mexico, and parts of the southern high plains, the atmosphere entered what fire meteorologists call extreme fire weather conditions, the highest operational tier before active wildfire catastrophe begins. Temperatures climbed toward 100 degrees while humidity collapsed into the single digits. Strong downslope winds accelerated eastward off the Rockies, warming and drying even further as they descended toward the plains. Grasslands, already weakened by months of drought, became critically receptive to ignition. In some locations, fuel moisture values resembled conditions more common in midsummer than spring. The atmosphere above the region behaved like a giant drying machine. Every gust pulled additional moisture from vegetation. Every hour of sunlight baked the ground harder. And because the same Rosby wave remained nearly stationary overhead, the dangerous conditions persisted far longer than normal daily weather cycles would usually allow. Fire agencies across multiple states pre-positioned crews and equipment, fully aware that under these atmospheric conditions a single spark could evolve into a fast-moving mega-fire within hours. The terrifying reality of wildfire behavior is that once fuels become critically dry, fire no longer spreads gradually. It begins creating its own weather. Flames generate powerful convection columns capable of producing ember storms, fire whirls, and localized wind systems that accelerate spread unpredictably. Scientists studying major fires over the last decade have repeatedly found that many modern wildfire disasters were amplified by persistent atmospheric blocking, patterns very similar to the one unfolding now. And once again, the key mechanism was synchronization. The same drought amplifying the East Coast heat dome through soil moisture feedbacks was also preparing fuels for ignition in the southern plains. The same descending air strengthening the ridge in one region was intensifying dryness in another. One wave, multiple consequences. The atmosphere was no longer producing isolated weather anomalies. It was behaving like a connected chain reaction stretching across the continent. And the deeper researchers looked into recent climate records, the more often they found this exact signature repeating. Slow-moving amplified waves producing simultaneous extremes across multiple regions at the same time. The question scientists could no longer ignore was simple. If these resonance events continue increasing in frequency, how long can modern infrastructure continue functioning under a climate system designed to deliver multiple major disasters simultaneously instead of separately? While fire danger expanded across the southern plains and snow-buried parts of Wyoming, another consequence of the same atmospheric wave began unfolding farther east. Across Missourian sections of the lower Midwest, repeated thunderstorms started moving over the same locations again and again and again, a process meteorologists call training. To people on the ground, it felt as if the sky had become stuck. Rain fell for hours over already saturated soil, while rivers slowly climbed beyond their banks. Small creeks transformed into fast-moving channels, carrying debris through low-lying roads and neighborhoods. Flash flood warnings multiplied across counties that had already received weeks of above-normal rainfall earlier in the season. And once again, the atmosphere was behaving exactly the way resonance theory predicts. On the eastern side of the trough, a strong low-level jet pulled warm moist air northward from the Gulf of Mexico. But instead of quickly progressing eastward like a normal spring storm system, the amplified Rosby wave slowed the entire structure almost to a crawl. Storms repeatedly regenerated along the same boundary zones, continuously feeding on warm humid air flowing north beneath colder air aloft. This process allowed rainfall totals to accumulate far beyond what a single thunderstorm complex would normally produce. In some regions, the atmosphere effectively became a conveyor belt of moisture. The dangerous part about flood events like this is not only the rainfall itself. It is persistence. Modern drainage systems, reservoirs, levees, and urban infrastructure are usually designed around storms that move. But stationary wave patterns create storms that linger. And when the atmosphere stops moving normally, hazards compound rapidly. Saturated soil loses its ability to absorb additional rainfall. Rivers rise faster. Transportation corridors fail earlier. Emergency response becomes more difficult because multiple flood zones emerge simultaneously across large geographic regions. Scientists studying recent flood disasters have increasingly identified atmospheric blocking and slow-moving Rosby wave configurations as major contributors to extreme rainfall persistence. And as global temperatures rise, the atmosphere itself can now hold more water vapor than it could decades ago. Warmer air increases evaporation. Increased evaporation loads the atmosphere with additional moisture. When storms finally release that moisture, rainfall rates become more intense. So the atmosphere is changing into dangerous ways simultaneously. The waves are slowing down, and the air inside those waves is carrying more water. The result is a climate system increasingly capable of producing prolonged rainfall events beyond historical infrastructure expectations. But perhaps the strangest part of all was that while floodwaters rose in Missouri, skies remained nearly cloudless beneath the eastern heat dome and snow continued falling in parts of the Rockies. One atmospheric wave for completely different disasters, all operating at once. The atmosphere does not think. It does not plan. It does not choose where disasters happen. But it does remember energy. Every drought, every warming ocean, every heat wave, every year of abnormal temperatures leaves fingerprints inside the climate system. Oceans store heat. Soil stores moisture deficits. Ice loss alters temperature gradient. And over time, those accumulated changes begin influencing how the atmosphere behaves on planetary scales. This is one of the reasons scientists became so concerned while analyzing the recent wave pattern. The atmosphere did not amplify in isolation. It amplified into preloaded conditions that had been building quietly for months and, in some cases, decades. Across large parts of North America, drought conditions had already reduced soil moisture well below historical averages. Dry soil matters because moisture normally acts like a cooling system for the land surface. When sunlight strikes wet ground, much of that energy goes into evaporation. But when the ground is dry, far more energy converts directly into heat. That means drought can intensify heat waves dramatically through a feedback loop called soil moisture-atmosphere coupling. The land becomes hotter faster because it has lost its evaporative buffer. And once extreme heat develops, the atmosphere removes even more moisture from the ground, strengthening the cycle further. Meanwhile, the North Atlantic Ocean had been running exceptionally warm for months before this event developed. Warm ocean surfaces transfer additional heat and moisture into the lower atmosphere, influencing large-scale pressure systems like the Bermuda High. Stronger subtropical ridges can then help anchor heat domes farther west and farther north than normal. At the same time, the Pacific Ocean was transitioning away from La Nina conditions toward a more neutral, or potentially El Nino-favored state, subtly shifting jet stream positioning across the northern hemisphere. None of these factors alone created the atmospheric event, but together, they loaded the climate system with instability before the Rosby wave even amplified. This is why modern climate extremes increasingly behave less like isolated events and more like chain reactions. The atmosphere is carrying more background energy than it used to. The oceans are warmer. The land is drier in many regions. Snowpack melts earlier. Heat arrives sooner. And when a large-scale wave pattern locks into place, all those hidden imbalances suddenly interact at once. Scientists sometimes describe this as loading the dice. Individual weather events still occur naturally, but the probabilities surrounding them begin shifting toward more extreme outcomes. That does not mean every year becomes catastrophic. But it does mean the atmosphere becomes more capable of producing synchronized anomalies beyond 20th century expectations. And quietly, almost unnoticed outside scientific circles, researchers have begun observing a troubling pattern emerging from recent decades of climate data. The atmosphere appears increasingly willing to enter states it once reached only rarely. For most of human history, civilizations assumed the atmosphere behaved like a background system. Storms came and went. Seasons rotated forward. Heat waves and droughts eventually broke. The sky always moved on. But over the last 15 years, scientists began noticing something unusual hidden inside the global record of extreme weather events. The atmosphere was not only becoming warmer. In certain situations, it was becoming slower. The first major warning sign arrived during the summer of 2010, when an immense heat dome mocked over western Russia while catastrophic flooding submerged parts of Pakistan. More than 50,000 people died across both disasters combined. Crops failed. Wildfires exploded around Moscow. Entire regions of Pakistan disappeared underwater beneath monsoon rainfall, intensified by atmospheric blocking. At first, many researchers treated the events separately. But as scientists reconstructed the upper-level circulation pattern, a startling picture emerged. Both disasters were connected to the same amplified Rosby wave structure, stretching across Eurasia. One wave, two extremes, thousands of miles apart. Then similar patterns appeared again. Europe's deadly heatwaves in 2018. Simultaneous crop failures across multiple northern hemisphere breadbasket regions. Persistent droughts in western North America. The extraordinary Pacific Northwest heat dome of 2021, where temperatures in parts of Canada reached levels previously considered almost impossible so far north. Again and again, researchers found the same signature hiding in the atmospheric data: large, slow-moving planetary waves remaining locked in place for abnormal periods of time. And the consequences were enormous because modern civilization depends heavily on geographic separation of disasters. One region fails, another compensates. One agricultural zone struggles, another produces surplus. One energy grid experiences stress while another remains stable. But synchronized extremes threaten that balance entirely. If multiple major food-producing regions experience heat and drought simultaneously, global grain supplies tighten rapidly. If several population centers experience dangerous heat at once, power demand spikes across entire continents simultaneously. If flood, fire, drought, and heat occur together, emergency management systems become overloaded in ways they were never designed to handle. This is why researchers studying atmospheric resonance have become increasingly concerned about what they call compound events, disasters that interact with one another instead of occurring independently. And perhaps most unsettling of all, observational data increasingly suggests these synchronized wave patterns may be appearing more often than many climate models originally projected. The atmosphere is still obeying the laws of physics. But the background conditions beneath those laws are changing. And when the atmosphere enters resonance now, it enters resonance inside a world carrying more heat, more moisture imbalance, and more stored climate energy than the civilizations before us ever experienced. Far from the tornadoes, the blizzards, and the fire corridors, another part of this story had already been unfolding silently for years across the Atlantic Ocean. Sea surface temperatures in large sections of the North Atlantic had climbed far above long-term averages, reaching levels that stunned many climate researchers. Satellite measurements and buoy observations repeatedly showed marine heat anomalies persisting month after month, even during seasons when ocean temperatures would normally cool. At first glance, the ocean may seem disconnected from the heatwave unfolding over the eastern United States. But in reality, the atmosphere and the ocean are deeply coupled systems, constantly exchanging energy. Warm oceans release additional heat and moisture into the air above them. That heat influences pressure systems, storm tracks, and the positioning of large-scale ridges. And during this event, the western Atlantic appeared to help strengthen the subtropical ridge parked offshore of the east coast. Meteorologists often call this feature the Bermuda High, a semi-permanent high-pressure system that plays a major role in shaping summer weather across eastern North America. When the Bermuda High strengthens and expands westward, it traps hot air beneath descending atmospheric motion. Clouds diminish. Solar heating intensifies. Warm air from the south surges northward. Heat begins accumulating day after day. Under ordinary conditions, passing troughs eventually disrupt the pattern and allow cooler air to return. But, under amplified Rosby wave resonance, the ridge can remain anchored far longer than normal. The atmosphere essentially becomes stuck in a feedback loop. The ridge strengthens the heat. The heat dries the land. The dry and intensifies the heat further. And all the while, warm Atlantic waters continue feeding additional energy into the lower atmosphere offshore. Scientists are still debating the exact contribution of ocean warming to these persistent ridge patterns, but many agree on one critical point. Warmer oceans increase the probability that the atmosphere can sustain stronger heat anomalies once blocking begins. In other words, the Atlantic did not create the wave, but it may have helped the wave hold its shape longer and amplify more intensely. And this raises a larger concern emerging across climate science today. The atmosphere is no longer operating over 20th century oceans. It is operating above oceans carrying enormous amounts of excess heat accumulated over decades of global warming. More than 90% of the excess heat trapped by greenhouse gases ultimately ends up stored in the oceans. That heat does not disappear. It waits. It reshapes pressure gradients. It alters evaporation patterns. It changes the background state beneath every storm and every atmospheric wave. Which means the next time the jet stream stalls into resonance, it may do so over oceans, even warmer than today's. And if that happens, the atmosphere may discover entirely new ways to amplify the extremes already beginning to emerge across the modern world. Long before the atmosphere locked into this extraordinary wave pattern, the land beneath it had already begun changing. Across large portions of North America, soil moisture levels had been steadily declining through months of persistent drought and abnormal warmth. Rivers ran lower than expected for spring. Snowpack melted earlier in the season. Vegetation entered stress sooner. And beneath the surface, the ground itself slowly lost one of its most important climate functions, the ability to cool the air above it. Most people imagine drought simply as lack of rain. But scientifically, drought is something much deeper. It is an energy imbalance between the land and the atmosphere. Under healthy conditions, wet soil absorbs solar energy and releases much of it through evaporation. That process acts like natural air conditioning for entire regions. But when the soil dries out, the energy has nowhere to go except directly into heating the air. The land begins converting sunlight into sensible heat instead of latent heat. Temperatures rise faster. Heat waves intensify more easily. And once the atmosphere becomes hotter, it removes even more moisture from the ground, creating a feedback loop capable of amplifying regional climate extremes dramatically. This is one of the hidden reasons the eastern heat dome became so intense this week. The atmosphere did not arrive over a neutral landscape. It arrived over preconditioned dry ground already primed to accelerate warming. Scientists studying historical heat disasters have repeatedly found the same mechanism operating beneath many of the most severe events in modern history, including the Dust Bowl summers of the 1930s and several major European heatwaves over the last decades. Dryl unloads the atmosphere toward extreme heat. And once large-scale atmospheric blocking traps that heat in place, temperatures can escalate beyond what the incoming air mass alone would normally produce. The troubling part is that drought itself is becoming increasingly persistent in many regions due to warming temperatures and shifting precipitation patterns. In some areas of western North America, researchers now describe the last decades as a mega drought, one of the driest long-term periods in over 1,000 years based on tree ring reconstructions. And although individual wet years still occur, the background drying trend remains significant. This matters because the atmosphere remembers land conditions. A continent entering summer already carrying widespread moisture deficits becomes far more vulnerable when amplified wave patterns develop overhead. And during this event, the atmosphere found exactly those conditions waiting beneath it. Perhaps the most unsettling part of this entire story is not the weather itself. It is the possibility that the climate models may have underestimated how often these patterns could occur. Climate models are among the most sophisticated scientific tools humanity has ever created. They simulate atmospheric circulation, ocean currents, radiation balance, cloud physics, and countless interactions across the Earth system. And for decades, they have successfully projected many large-scale warming trends observed today. But in recent years, some researchers began noticing a troubling discrepancy. Observations of amplified Rosby wave events appeared to be increasing faster than certain model ensembles predicted. In other words, the real atmosphere seemed more willing to enter persistent resonance states than some simulations expected. Scientists believe part of the problem may involve how models represent jet stream dynamics and upper-level wave amplification. Many climate models reproduce broad warming trends very accurately while still struggling with the precise frequency and persistence of blocking patterns. Small differences in wave behavior can produce enormous differences in real-world outcomes because once a planetary wave locks into place, hazards compound rapidly across multiple regions at once. Researchers studying synchronized crop failures and concurrent heat extremes have repeatedly found that observed atmospheric behavior in recent decades sometimes exceeds modeled expectations. That does not mean the models are useless. Far from it. In fact, modern climate science remains extraordinarily robust. But it does mean the atmosphere may contain amplification behaviors not yet fully captured by current simulations. And this possibility deeply concerns many scientists because civilization increasingly depends on predictive planning. Infrastructure, agriculture, insurance systems, emergency management, water allocation, and energy grids all rely on statistical expectations built from historical climate behavior and modeled future probabilities. But if resonance events occur more frequently than expected, those systems may face stress levels beyond what planners assumed possible. The atmosphere would essentially be moving faster than adaptation efforts. And perhaps most unsettling of all, these changes do not arrive dramatically at first. They emerge quietly through strange seasons, unusual anomalies, synchronized disasters, and phrases buried inside forecast discussions that only specialists fully understand. Near the edge of climatology, persistent blocking, statistically extreme, small signals scattered across years. Until eventually, a realization begins forming inside the scientific community. The atmosphere is not behaving exactly like it used to. And the event unfolding this week may become remembered as one of the moments when that realization became impossible to ignore. The frightening truth about atmospheric change is that it rarely announces itself all at once. The atmosphere teaches new behavior slowly, first through anomalies, then through repeated anomalies, then through patterns that scientists initially describe as unusual before quietly realizing those patterns are beginning to repeat. This is how climate transitions often reveal themselves. Not through a single catastrophic day, but through the gradual normalization of extremes that once seemed impossible. During the last several summers, researchers across North America, Europe, and Asia began documenting an increasing number of events linked to stalled wave patterns and persistent atmospheric blocking. Heat domes lingered longer. Wildfire smoke traveled farther. Flood-producing storms remained stationary for days instead of hours. In some years, multiple agricultural regions experienced damaging heat simultaneously, reducing crop yields across continents at the same time. What made these events especially alarming was synchronization. Historically, weather extremes tended to remain regionally isolated, but resonance patterns create continent-scale coordination inside the atmosphere itself. One stationary wave can simultaneously intensify heat in one region, flood another, dry out a third, and destabilize severe storm environments somewhere else. The atmosphere begins behaving less like independent local weather systems and more like one interconnected planetary engine. Scientists studying these patterns increasingly warn that the risks extend far beyond meteorology. Modern civilization depends on geographic diversity to absorb shocks. If drought harms one crop region, another compensates. If one power grid experiences stress, neighboring systems assist. But synchronized extremes remove those buffers. Multiple systems fail simultaneously. Insurance markets strain under overlapping disasters. Food prices surge globally. Transportation networks weaken under repeated climate disruptions. And because these resonance events can persist for days or weeks, recovery becomes far more difficult. What happened this week was not merely unusual weather. It was a demonstration of how a single amplified atmospheric wave can activate multiple vulnerabilities across an entire continent at once. And perhaps the most unsettling detail of all is this: the atmosphere achieved these extremes before summer has even fully begun. The wave developed in May, during a seasonal transition period that historically carries lower thermal energy than peak summer months, which raises a deeply uncomfortable possibility. If the atmosphere can already produce this level of amplification now, what happens later in the season when ocean temperatures rise even further? Soils dry out more aggressively, and the northern hemisphere accumulates maximum solar heating. Some researchers fear the most dangerous resonance patterns may still lie ahead later in the century's warmer summers, because every year the baseline shifts slightly upward. Every year the atmosphere operates over warmer oceans, altered snowpack timing, and greater moisture imbalance. And slowly, almost invisibly, the sky learns new patterns. Most people never see the true shape of the atmosphere. They experience only fragments of it through local forecasts, isolated storms, or brief weather alerts flashing across their phones. But high above the Earth, the atmosphere operates as a continuous interconnected fluid wrapping around the entire planet. Every storm system, every heat wave, every drought, every flood is part of that larger circulation. And during resonance events, the hidden architecture of that circulation suddenly becomes visible through synchronized extremes unfolding across enormous distances simultaneously. This is why meteorologists were so disturbed by the wave structure this week. Not because blizzards are impossible in May, not because tornadoes occur in the plains, not because heat waves happen in the east. All of those events individually remain scientifically understandable. The disturbing part was that all of them emerged together from one planetary-scale atmospheric configuration. The atmosphere effectively revealed its underlying geometry. One ridge amplified northward over the east coast. One trough plunged southward into the Rockies. Moisture surged northward through the plains while descending dry air accelerated over the southern high plains. The entire continent became divided into interacting zones controlled by one locked wave pattern. Scientists sometimes compare these atmospheric structures to standing waves in physics, where energy becomes trapped instead of freely propagating forward. When this happens in the atmosphere, the consequences can persist for extraordinary periods of time. Heat accumulates beneath ridges. Storms repeatedly track across the same regions. Dry areas become drier. Wet regions become wetter. And because the atmosphere remains nearly stationary, feedback loops intensify every hazard underneath them. This week's event may eventually become historically important, not simply because of the extremes themselves, but because it demonstrated how modern climate risks increasingly emerge through interconnected systems rather than isolated disasters. Heat influences drought. Drought influences wildfire. Ocean warming influences ridge behavior. Blocking patterns influence flood persistence. Everything interacts. And perhaps this is the most difficult reality for modern civilization to emotionally process. Humanity evolves psychologically to understand immediate local threats. A storm approaching town, a river rising nearby, smoke visible on the horizon. But resonance events operate on scales larger than ordinary human intuition. They unfold across entire continents and evolve through invisible atmospheric mechanics few people ever see directly. The danger is not only physical, it is cognitive. Civilization still communicates disasters as separate stories while the atmosphere increasingly behaves as one interconnected system. And somewhere inside that mismatch lies one of the greatest challenges humanity may face during the coming century. Learning to understand the atmosphere not as isolated weather, but as a living planetary engine capable of synchronizing extremes across the world, all at once. One of the strangest aspects of this event was not what happened in the sky. It was the language experts began using to describe it. Meteorologists are trained to remain measured, technical, and cautious. Operational forecast discussions are normally written in restrained scientific terminology designed to communicate risk without emotional exaggeration. But during this wave event, something subtle changed inside those discussions. Phrases appeared that carried unusual weight for professionals who spend their careers interpreting atmospheric behavior. Approaching the upper edge of climatology. Highly anomalous. Rare for this time of year. Potentially historic. To most people, these phrases sound routine. But inside meteorology, they signal discomfort. They signal that the atmosphere is entering statistical territory that forecasters rarely encounter. Scientists understand probability distributions deeply. They know what seasonal ranges normally look like. They know how often certain atmospheric configurations should appear within a historical baseline. And what disturbed many researchers this week was not simply the intensity of individual extremes, but how many extremes were happening together under one amplified wave. Quietly inside weather offices and climate research centers, conversations began shifting toward a larger realization. The atmosphere may now be capable of entering high-energy synchronized states more often than historical records alone would suggest. This is important because civilization's infrastructure is fundamentally built on probability. Bridges are engineered around flood expectations. Power grids are designed around historical heat demand. Reservoir systems depend on projected snowmelt timing. Insurance industries calculate risk from past climate statistics. Agriculture depends heavily on seasonal predictability. But when atmospheric behavior begins shifting outside historical distributions, the assumptions beneath those systems become less stable. And the atmosphere does not need to become permanently catastrophic to create enormous disruption. It only needs to produce synchronized extremes slightly more often than expected. That alone is enough to strain emergency response systems, destabilize food markets, increase insurance losses, and stress infrastructure beyond design assumptions. Scientists studying climate resilience increasingly warn that the danger of the 21st century may not come from single apocalyptic events. Instead, it may emerge through repeated compound stresses accumulating faster than societies can adapt. Heatwaves arriving earlier, droughts lasting longer, floods becoming more persistent, fire seasons overlapping with severe storm seasons, and above all, the increasing possibility that multiple hazards may occur simultaneously instead of independently. This is why the wave pattern this week mattered so much scientifically. It acted like a demonstration of how interconnected modern climate risks are becoming. One planetary-scale atmospheric structure activated multiple disasters across thousands of miles at the same time. And perhaps most unsettling of all, the atmosphere achieved this configuration without even reaching peak summer energy yet. The season is still young. The oceans are still warming. The soil moisture deficits are still evolving. The atmosphere may still be building toward even stronger resonance patterns later in the year. And somewhere inside forecast centers tonight, scientists are already watching the next wave beginning to organize over the Pacific. Far out over the Pacific Ocean, thousands of miles from the blizzards, tornadoes, and heat domes affecting North America, Another shift was quietly unfolding beneath the surface of the water. Sea surface temperatures across the equatorial Pacific were beginning to transition away from prolonged La Nina conditions toward a more neutral and potentially El Nino-favored state. To most people, this change sounds abstract. But for climate scientists, ENSO transitions are among the most important drivers of planetary-scale atmospheric behavior on Earth. ENSO, short for the El Nino, Southern Oscillation, influences the position of tropical convection, jet stream patterns, rainfall distribution, and storm tracks across huge portions of the globe. During La Nina years, cooler waters dominate the eastern Pacific, often strengthening certain atmospheric circulation patterns. During El Nino, warmer waters shift convection eastward and alter how energy moves through the atmosphere. But transition years are sometimes the most volatile of all because the atmosphere enters a temporary state of instability while circulation patterns reorganize. Historically, several major amplified ridge events across North America occurred during ENSO transition periods. Scientists believe part of the reason involves shifting subtropical jet dynamics and changing tropical heat distribution across the Pacific Basin. The atmosphere becomes more susceptible to unusual wave amplification while trying to rebalance itself. That does not mean ENSO alone caused this event. Climate systems are never driven by one factor in isolation. But the Pacific transition may have acted like another layer of preconditioning beneath the larger resonance pattern. Warm Atlantic waters, dry continental soils, Arctic amplification, ENSO transition dynamics. None of them individually explain the event. Together, they created a background state unusually favorable for atmospheric amplification. And this is what makes modern climate science both fascinating and terrifying. The atmosphere is not responding to one single variable. It is responding to multiple interacting changes unfolding simultaneously across oceans, land surfaces, ice systems, and atmospheric circulation itself. The climate system is becoming more interconnected in its extremes. One region's ocean anomaly influences another continent's heat wave. Arctic warming alters mid-latitude jet behavior. Drought amplifies local heating, which then feeds back into atmospheric stability and wave persistence. Every component interacts with every other component. And when enough of those interactions align at the same time, the atmosphere can suddenly reorganize into patterns powerful enough to reshape weather across entire hemispheres. This is why researchers increasingly describe climate change not merely as warming, but as destabilization of large-scale energy distribution throughout the Earth system. The atmosphere is still seeking balance. But the conditions beneath that balance are shifting faster than human civilization has ever experienced before. And somewhere tonight, hidden inside streams of satellite data and forecast model simulation, scientists are trying to determine whether the next amplified wave is already beginning to fall. One of the most dangerous misconceptions about climate extremes is the belief that once a heat wave ends, the system resets back to normal. But the atmosphere rarely releases energy completely anymore. Heat lingers in the oceans. It lingers in drought-stricken soil. It lingers in urban infrastructure that absorbs sunlight during the day and slowly releases it through the night. And over time, these lingering reservoirs begin changing the baseline from which future extremes emerge. Scientists have started observing this phenomenon across multiple regions of the world. Heat waves are not only becoming hotter. In many cases, nighttime temperatures are remaining elevated for longer periods, preventing ecosystems, infrastructure, and human bodies from fully recovering between events. This matters enormously because nighttime cooling is one of the planet's most important natural recovery mechanisms. Crops cool down overnight. Asphalt releases accumulated energy. Human cardiovascular systems stabilize during sleep. But under persistent ridging and warmer background temperatures, the recovery window shrinks. Cities remain trapped beneath warm stagnant air long after sunset. Concrete radiates stored heat back into neighborhoods. Air conditioning demand remains elevated through the night, stressing electrical grids continuously instead of temporarily. The atmosphere begins behaving less like a sequence of separate heat events and more like a sustained accumulation of thermal stress. During this week's wave pattern, overnight temperatures in some urban corridors remained abnormally high, even after sunset, because the heat dome trapped warm air near the surface while weak winds prevented efficient cooling. Meteorologists increasingly refer to this as heat retention feedback. The atmosphere stores heat more effectively once certain thresholds are crossed. And warmer oceans amplify the process further because coastal regions lose access to historically cooler marine air masses. Scientists studying urban climate systems now warn that many cities were designed around 20th century nighttime cooling assumptions that may no longer hold reliably during future resonance events. Buildings, power systems, transportation infrastructure, and even emergency response protocols depend heavily on the expectation that nights provide recovery. But what happens when the atmosphere stops cooling efficiently? What happens when heat becomes persistent instead of episodic? This is one of the hidden dangers researchers worry about most. Not singular catastrophic days, but cumulative physiological stress building over weeks of repeated amplified patterns. The atmosphere does not need to become unsurvivable everywhere to become deeply destabilizing for civilization. It only needs to remain abnormally stressed for longer periods than human systems were designed to tolerate. And the frightening reality emerging from modern climate observations is that the Earth system appears increasingly capable of trapping and redistributing heat in ways modern civilization has never experienced before. Most people experience climate through weather. A hot day, a storm warning, smoke in the distance. But civilization experiences climate through food, through harvest timing, through soil moisture, through river flow, through crop survival under prolonged stress. And this is why atmospheric resonance events frighten agricultural scientists so deeply. Modern food systems depend heavily on geographic diversity. If one farming region struggles, another usually compensates. But synchronized atmospheric waves threaten multiple agricultural zones simultaneously. During major resonance years, extreme heat can strike several grain-producing regions across the northern hemisphere at the same time. Drought intensifies evaporation. Heat accelerates crop stress during critical growth periods. Pollination fails more frequently under abnormal nighttime warmth. And persistent atmospheric blocking prevents relief systems from arriving quickly enough to stabilize conditions. Researchers studying recent decades have already identified increasing correlations between amplified Rosby wave events and concurrent crop reductions across major breadbasket regions. Wheat yields decline simultaneously in Europe and Western Russia. Corn stress intensifies across North America while heat affects sections of Asia. The atmosphere effectively synchronizes agricultural vulnerability across continents. This matters because global food systems operate on narrow margins. Modern civilization feeds billions of people through highly interconnected trade networks optimized for efficiency, not resilience. Small percentage losses across multiple regions can rapidly influence global grain prices, political stability, and food access for vulnerable populations. Historically, societies survived local agricultural failures because neighboring regions remained productive. But synchronized extremes weaken that buffer. And perhaps most unsettling of all, resonance events can emerge very quickly. A wave locks into place. Heat persists. Rainfall disappears. Soil moisture collapses. Within weeks, crop stress indicators begin climbing across multiple nations simultaneously. Scientists increasingly warn that climate risk should not be understood only through isolated disasters. It must also be understood through cascading systems failure. Transportation depends on stable infrastructure. Infrastructure depends on energy. Energy depends on water availability and temperature stability. Food production depends on all of them simultaneously. And overhead, the atmosphere links everything together through invisible circulation patterns spanning entire hemispheres. During this week's wave event, the synchronized hazards unfolding across the United States offered a smaller preview of how these compound risks operate. Heat, drought, flooding, wildfire conditions, and severe storms all interacting beneath one planetary scale pattern. Now imagine similar resonance structures extending across multiple continents during future decades of additional warming. This is the possibility increasingly discussed within climate research circles. Not a single apocalypse, but a gradual rise in synchronized stress events capable of destabilizing systems modern civilization once assumed were geographically protected from one another. Modern cities were not designed for the atmosphere that is beginning to emerge. Most urban infrastructure across the world was engineered using historical climate assumptions developed during the 20th century. An era when heat waves were shorter, wildfire seasons were smaller, flood probabilities were lower, and synchronized continental extremes were far less common. Roads, bridges, drainage systems, electrical grids, and water infrastructure all depend on probability calculations rooted in past weather behavior. But when the atmosphere shifts outside those historical ranges, entire urban systems begin experiencing stress simultaneously. During this recent wave event, electrical demand surged across major East Coast cities as millions relied on air conditioning far earlier in the season than normal. Grid operators monitored transformer loads closely while temperatures remained elevated through the night. In parts of the Midwest, flood risks threatened transportation corridors already stressed by severe storms. Farther west, wildfire danger expanded beneath hot, dry winds while mountain snow disrupted highways that should have already transitioned into spring conditions. None of these events individually collapsed infrastructure, but together they exposed a larger vulnerability. Cities are highly interconnected systems. Transportation depends on electricity. Electricity depends on cooling capacity and stable transmission networks. Water systems depend on reliable power and predictable precipitation cycles. Healthcare systems depend on transportation, access, and temperature stability. Once multiple climate stresses occur at once, resilience becomes far more fragile than most people realize. Scientists increasingly describe this as systemic climate vulnerability. The danger no longer comes only from isolated disasters overwhelming one city at a time. The danger emerges when multiple regions experience different disasters simultaneously under one large-scale atmospheric pattern. Emergency resources become stretched. Insurance losses compound. Supply chains slow. Energy demand spikes across huge areas at once. And because resonance events can persist for days or weeks, systems have less recovery time between stresses. This is especially concerning for older urban regions built long before modern climate risks were fully understood. Stormwater systems sized for historical rainfall frequencies may fail during repeated training thunderstorms. Electrical grids designed around 20th century heat distributions face rising nighttime cooling demand. Transportation infrastructure experiences thermal stress under prolonged heat that earlier engineering standards rarely anticipated. The atmosphere is not attacking cities intentionally, but the climate assumptions those cities were built upon are beginning to shift. And quietly, in engineering offices and climate adaptation centers around the world, planners are confronting a difficult reality. The atmosphere modern civilization evolved under may no longer be the atmosphere modern civilization will operate within during the coming century. Even as attention focused on blizzards, tornadoes, and heat domes across land, another transformation was unfolding above the oceans. The marine atmosphere itself has begun changing in ways scientists are only starting to fully understand. Ocean temperatures across large portions of the world have reached record or near record levels during recent years, especially in the North Atlantic and sections of the Pacific. And because the atmosphere and oceans constantly exchange energy, warmer oceans influence far more than coastal temperatures alone. They reshape evaporation patterns, humidity transport, storm intensity, and atmospheric stability across entire hemispheres. Warm water acts like stored climate fuel. Every additional degree of ocean warming increases evaporation into the lower atmosphere. That moisture does not remain harmlessly over the sea. Atmospheric circulation transports it across continents, feeding storms, heat waves, and precipitation extremes thousands of miles away. Scientists often describe the oceans as the planet's memory system because they absorb and retain enormous quantities of excess heat over long periods. More than 90% of the excess heat trapped by greenhouse gases eventually enters the oceans, which means the atmosphere above today's oceans operates inside a fundamentally different energy environment than it did decades ago. During this wave event, unusually warm Atlantic waters likely helped reinforce the subtropical ridge parked offshore of the east coast. But globally, marine heat waves are now appearing with increasing frequency across many ocean basins. Coral reefs bleach under prolonged thermal stress. Fish migration patterns shift. Atmospheric moisture transport intensifies. Tropical systems sometimes encounter warmer waters capable of supporting more rapid intensification. And perhaps most importantly, warmer oceans reduce one of the planet's historical stabilizing mechanisms. In the past, cooler oceans often moderated nearby heat extremes by supplying cooler marine air. But as sea surface temperatures rise, that moderating influence weakens. Coastal cities remain warmer overnight. Humid air masses retain more energy. Heat waves become harder to break. Scientists studying atmosphere-ocean coupling increasingly warn that future resonance events may become more powerful simply because the background oceans beneath them are warmer than any comparable period in modern civilization. The atmosphere is no longer interacting with 20th century oceans. It is interacting with oceans carrying decades of accumulated excess heat. And because ocean systems evolve slowly, much of that stored energy will continue influencing atmospheric behavior for years or even decades ahead. Which means the wave patterns scientists are studying today may represent only the early stages of a much larger climate transition still unfolding across the Earth system. There was a time when wildfire smoke remained mostly regional. A forest burned, nearby towns suffered, and eventually the atmosphere carried the smoke away. But in recent years, the scale of wildfire behavior has changed so dramatically that smoke itself has become a planetary phenomenon. During major fire seasons, smoke plumes now travel thousands of miles across continents and oceans, dimming skies far from the flames that created them. Cities wake beneath orange sunlight generated by fires burning hundreds or even thousands of miles away. Air quality collapses in regions with no local fire at all. And overhead, the atmosphere quietly redistributes the chemical remains of entire forests across the hemisphere. Scientists studying wildfire behavior increasingly describe modern megafires as coupled atmosphere fire systems. Under extreme heat, drought, and wind, fires become large enough to influence the atmosphere above them directly. Massive convection columns rise into the upper troposphere, generating pyrocumulonimbus clouds, thunderstorm-like structures capable of producing lightning, powerful downdrafts, and smoke injections reaching stratospheric heights. In some cases, wildfire plumes become visible from space as continent-scale atmospheric disturbances. During this recent resonance event, fire danger expanded across multiple regions simultaneously because the same atmospheric wave intensified drought, lowered humidity, and strengthened downslope winds beneath persistent ridging. This is one of the reasons synchronized atmospheric patterns are so dangerous. The atmosphere can create broad geographic corridors favorable for ignition all at once. And once fires begin under those conditions, suppression becomes extraordinarily difficult. Hot, dry air accelerates combustion. Wind alters ember transport. Drought weakens vegetation resilience. Heatwaves stress firefighters and infrastructure simultaneously. Everything compounds together. But perhaps the most unsettling aspect of modern wildfire behavior is what the smoke itself reveals. Smoke is evidence that ecosystems are crossing thresholds. Forests stressed by heat and drought burn differently than healthy forests. Fire seasons begin earlier and end later. Regions once considered relatively safe from major fire risk now experience repeated dangerous conditions. And because smoke particles interact with sunlight and cloud formation, large fire seasons may even influence regional atmospheric behavior themselves. The atmosphere is no longer merely reacting to climate change. In some regions, it is entering feedback loops where drought, heat, wildfire, and atmospheric chemistry increasingly reinforce one another. And overhead, invisible planetary waves continue redistributing those consequences across enormous distances, linking regions together through air currents few people ever think about until the sky itself changes color. Perhaps the strangest part of climate change is not the disasters themselves. It is adaptation. Human beings normalize conditions surprisingly quickly. A generation born into persistent wildfire smoke eventually accepts smoky summers as ordinary. Children raised during recurring heat emergencies begin treating extreme temperatures as part of seasonal life. Cities repeatedly flooded every few years slowly reorganize around disruption that earlier generations would have considered extraordinary. Civilization adjusts psychologically long before it fully adjusts physically. And this may become one of the defining experiences of the 21st century. The gradual normalization of atmospheric behavior that would once have seemed impossible. Scientists sometimes call this shifting baseline syndrome. Each generation unconsciously treats the conditions of its youth as normal, even when those conditions differ dramatically from previous historical baselines. Over time, societies lose intuitive awareness of how rapidly systems are changing because adaptation happens incrementally. But the atmosphere does not care about psychological normalization. Physics continues operating regardless of what humans emotionally accept. Oceans continue accumulating heat. Ice continues melting. Soil moisture continues shifting. Atmospheric circulation continues responding to altered energy balances across the Earth system. During this wave event, millions experienced conditions that historically would have seemed extraordinary for May, blizzards in one region, dangerous heat in another, synchronized severe weather and fire risk unfolding simultaneously across the continent. Yet within days, media cycles moved on. The atmosphere reset temporarily, and life continued. This is how climate transitions often unfold. Not through one singular apocalyptic moment, but through repeated extremes gradually absorbed into everyday expectations. The danger is that adaptation can create the illusion that systems remain stable, even while vulnerabilities deepen underneath. Infrastructure may continue functioning until multiple stresses arrive simultaneously. Agriculture may remain productive until several major breadbasket regions fail together. Insurance systems may absorb losses until compound disasters overwhelm actuarial assumptions. Civilization often appears resilient right up until critical thresholds are crossed. Scientists increasingly warn that the challenge ahead is not only reducing future warming, but increasing societal resilience to synchronized extremes already emerging today. Because even if global emissions declined rapidly tomorrow, much of the climate energy already stored in the oceans and atmosphere would continue influencing weather patterns for decades. The atmosphere modern children inherit will not behave exactly like the atmosphere their grandparents knew. And somewhere tonight, a child is growing up beneath skies shaped by amplified wave patterns, extreme heat, wildfire smoke, and shifting seasons that earlier generations would barely recognize. For them, this may become normal. But scientifically, historically, and atmospherically, the planet is still entering territory modern civilization has never fully experienced before. There is a strange psychological moment that happens during major atmospheric anomalies. The forecasts stop feeling believable, even when they are scientifically accurate. People look at the numbers and assume there must be a mistake. 98 degrees in May. Blizzard warnings beside heat advisories. Tornado outbreaks developing while wildfire danger reaches extreme levels elsewhere. The human brain instinctively rejects combinations it has rarely experienced before. And yet the atmosphere does not care what feels emotionally reasonable. It only follows physics. During this recent event, meteorologists across the country watched operational forecast models repeatedly verify against conditions that looked absurd only days earlier. Heat projections once considered overly aggressive became reality. Severe weather parameters reached values associated with major outbreaks. Snowfall totals in the Rockies climbed toward winter-like accumulations despite the advancing season. And as each forecast verified successfully, scientists were forced to confront an uncomfortable truth. The atmosphere was fully capable of producing these synchronized extremes under modern climate conditions. What once seemed theoretical was becoming operational reality. This is one of the reasons climate communication has become so difficult. Human intuition evolved inside relatively stable climate systems where seasonal expectations remained broadly reliable. Spring felt like spring. Summer arrived gradually. Extremes existed, but they usually remained separated in time and space. Modern atmospheric resonance patterns disrupt those expectations entirely. The atmosphere can now generate combinations that feel emotionally surreal while remaining scientifically explainable. And because the events are physically real, society must increasingly make decisions based on forecasts that psychologically feel impossible. The emergency managers must prepare for heat emergencies before schools have even finished spring schedules. Fire crews must mobilize under conditions resembling midsummer while mountain snow still blocks highways elsewhere. And it misses us. Electrical grids must absorb cooling demand during seasons historically associated with mild temperatures. Everything becomes slightly misaligned from historical timing. Scientists studying human perception of climate risk increasingly warn that one of the greatest dangers ahead may be cognitive lag. Civilization emotionally adapts slower than the atmosphere physically changes. People continue expecting the climate patterns they grew up with even while those patterns quietly shift beneath them. And during rare resonance events like this one, the gap between expectation and reality becomes impossible to ignore. Forecast maps begin looking unreal, but the atmosphere keeps verifying them anyway. At the center of this entire story lies one invisible structure circling the northern hemisphere, the jet stream. This high-altitude river of fast-moving air normally acts like a stabilizing boundary between colder polar air and warmer subtropical air. Under stable conditions, the jet stream flows relatively smoothly west to east, guiding storms steadily across continents. But the atmosphere is no longer operating under entirely stable conditions. The Arctic is warming far faster than lower latitudes, a phenomenon scientists call Arctic amplification. Sea ice declines exposed our ocean water, which absorbs more solar energy. Snow cover melts earlier. Polar regions retain more heat than they once did. And over time, this weakens the temperature contrast between the pole and the equator, one of the main forces driving jet stream intensity. Imagine a river losing part of the pressure gradient pushing it forward. The flow becomes slower, more unstable, and more prone to wandering. Some atmospheric researchers believe this weakening gradient may contribute to larger north-south meanders inside the jet stream, allowing Rosby waves to amplify more dramatically and move more slowly. The science remains actively debated, but observational trends increasingly suggest that persistent blocking patterns are becoming more influential during certain seasons. When the jet stream loses balance, the atmosphere behaves differently. Instead of moving weather systems efficiently across continents, the flow begins trapping them. Heat remains parked over one region. Storms repeatedly strike another. Dry air lingers beneath descending ridges while flood-producing systems stall elsewhere. The atmosphere starts acting less like a conveyor belt and more like a series of lock-pressure systems holding entire regions hostage beneath persistent conditions. During this recent wave event, the jet stream developed one of these highly amplified configurations. A deep trough plunged southward into the western United States, while an enormous ridge expanded over the east coast. Between them, severe storm environments intensified across the plains while fire danger expanded across dry regions beneath descending air. It was atmospheric imbalance expressed on continental scales. Scientists increasingly fear that future decades may bring more frequent episodes where the jet stream enters these exaggerated patterns for prolonged periods. And because warmer oceans and drier land surfaces add additional energy to the climate system, each resonance event may carry greater potential for extreme outcomes than similar patterns would have produced historically. The atmosphere is still obeying the same physical laws it always has, but the conditions underneath those laws are shifting rapidly. and as the balance inside the jet stream changes, the entire northern hemisphere may begin experiencing weather patterns that feel increasingly unfamiliar, unstable, and synchronized in ways human civilization has never fully encountered before. One of the clearest signs that the climate system is shifting is not simply hotter temperatures. It is the collapse of seasonal boundaries. Winter conditions appearing deep into spring. Summer heat arriving weeks early. Fire seasons overlapping with severe weather seasons. Flood seasons extending longer than historical norms. The atmosphere is beginning to blur the transitions that once separated the calendar into relatively stable phases. During this wave event, the collapse became impossible to ignore. Us. Blizzard conditions erupted in Wyoming while dangerous heat spread across the East Coast. Tornado outbreaks intensified across the plains while wildfire conditions expanded across the southern high plains. It felt less like one season replacing another and more like multiple seasons colliding simultaneously. Scientists increasingly describe this phenomenon as seasonal compression and overlap. As global temperatures rise, transitional periods like spring and autumn become more unstable because the atmosphere contains larger energy contrast over shorter time frames. Cold air masses still exist, especially at high latitudes and elevations, but warmer subtropical air now expands farther north earlier in the year. When those air masses collide beneath amplified wave patterns, the atmosphere can produce extraordinary contrasts across short distances. One side of the wave enters midsummer conditions, while another side falls backward into winter. Historically, seasonal transitions acted like buffers that gradually redistributed atmospheric energy across the hemisphere. But resonance events disrupt that progression. The atmosphere begins jumping between states instead of evolving smoothly. Heat arrives suddenly. Cold returns abruptly. Storm intensity escalates rapidly because larger thermal contrasts exist simultaneously within the circulation. This matters because ecosystems and infrastructure evolved around relatively predictable timing. Plants emerge based on seasonal cues. Snowpack melts according to expected warming patterns. Agricultural schedules depend on frost probabilities remaining relatively stable. Energy systems anticipate gradual demand shifts between heating and cooling seasons. But when the atmosphere begins overlapping seasons, those assumptions weaken. Early warmth can trigger premature plant growth vulnerable to returning cold outbreaks. Heat arriving before seasonal acclimatization increases health risks dramatically. Fire seasons expand into months historically considered safe. Severe weather overlaps with drought stress. The atmosphere becomes less orderly. And perhaps most unsettling of all, these changes often appear subtle at first. One strange spring, one early heatwave, one unusual snowstorm. But over time, the pattern repeats often enough that scientists begin recognizing a larger signal hidden beneath the individual event. The climate system is no longer transitioning between seasons as smoothly as it once did. And during resonance events, the atmosphere can briefly make the entire continent experience multiple seasons at once. Long after television weather broadcasts end and most cities fall asleep, scientists continue watching the atmosphere through an endless stream of satellite imagery, upper air soundings, pressure analyses, and forecast model simulations. Inside forecasting centers and research institutions around the world, glowing maps track the invisible architecture of the planet's circulation in real time. To the public, weather often feels chaotic. But to atmospheric scientists, the sky reveals patterns. Waves, pressure gradients, temperature anomalies, moisture transport corridors, signals hidden inside movement. During this event, many researchers were not simply watching surface conditions. They were watching the geometry of the atmosphere itself. On upper-level charts, the Rosby wave appeared like a massive deformation wrapped across North America. One ridge towering northward over the east coast, one trough diving deep into the western states. Between them, energy rotated through the plains while moisture surged northward from the Gulf of Mexico. The atmosphere looked less like random weather and more like a locked mechanical structure stretching across the continent. Scientists pay especially close attention to what are called 500 millibar height anomalies, maps showing the behavior of the middle atmosphere roughly 18,000 feet above Earth. This layer reveals the true shape of planetary waves. Under ordinary conditions, the patterns move steadily eastward. But during resonance events, the anomalies stall and intensify. Ridges strengthen, troughs deepen. The atmosphere becomes trapped in repeating circulation. And once researchers see that locking process begin, concern rises quickly because they know the consequences below can escalate for days afterward. Heat intensifies beneath ridges. Storm tracks stall. Flooding expands. Fire conditions worsen. Everything becomes persistent. Some scientists now compare these atmospheric maps to medical imaging for the planet itself. They reveal the hidden circulatory system controlling weather across entire hemispheres. And increasingly, researchers are noticing patterns they did not expect to see so frequently during the early 21st century. More amplified waves, more persistent blocks, more synchronized extremes. None of this means every season becomes catastrophic. The atmosphere still fluctuates naturally. Quiet periods still occur. Stable weather still exists. But the probability landscape underneath the atmosphere appears to be shifting. The sky is entering configurations once considered rare more often than historical experience alone would suggest. And somewhere tonight, while most of the world sleeps unaware, scientists continue studying the next wave already forming over the Pacific, trying to answer a question nobody yet fully understands. How often can the atmosphere continue doing this before the climate system itself begins behaving fundamentally differently than the civilization beneath it was built to expect? Far beneath the storms and heat domes of the atmosphere, another system is quietly moving enormous amounts of energy around the planet here. It flows through the Atlantic Ocean like a hidden conveyor belt, transporting warm water northward and colder water southward in a circulation scientists call the Atlantic Meridional Overturning Circulation, or IMOC. For thousands of years, this current has helped regulate climate across the northern hemisphere. It moderates temperatures in Europe, influences storm tracks, affects rainfall patterns, and plays a critical role in distributing heat throughout the oceans. But in recent decades, researchers have become increasingly concerned that this circulation may be weakening. Fresh water from melting Greenland ice and increased Arctic precipitation is reducing the salinity of northern Atlantic waters. That matters because the AMOC depends partly on cold, salty water becoming dense enough to sink deep into the ocean, driving the circulation forward. As salinity decreases, the system may slow. The science remains complex and actively debated, but multiple studies suggest the circulation is weaker now than during much of the 20th century. Why does this matter for atmospheric resonance? Because oceans and atmosphere are tightly linked. Changes in Atlantic circulation alter sea surface temperature patterns, which influence pressure systems and jet stream behavior above them. Some researchers believe warming patterns in the North Atlantic may already be contributing to altered atmospheric blocking configurations near Europe and Eastern North America. In simple terms, the atmosphere may be responding not only to greenhouse warming directly, but also to changing ocean circulation underneath it. During this recent wave event, unusually warm Atlantic waters likely helped support persistent ridge near the east coast. But on longer timescales, scientists worry that disruptions in ocean heat transport could further destabilize atmospheric patterns across the northern hemisphere. The frightening part is that ocean systems evolve slowly. They store climate memory over decades and centuries, which means some of the atmospheric changes unfolding today may actually be responses to oceanic shifts that began years ago. And because the oceans absorb most of the excess heat trapped by greenhouse gases, their influence on future atmospheric behavior will likely continue growing. Civilization tends to experience climate through storms, fires, and heat waves. But beneath all of those visible events, the oceans remain the deeper engine quietly shaping the atmosphere from below. And if those oceanic engines continue changing, the sky above them may continue changing too. There is a reason many climate scientists sound cautious, even when discussing deeply alarming trends. Science depends on evidence, uncertainty ranges, and careful language. Researchers are trained not to exaggerate. They speak in probabilities, confidence intervals, and modeled scenarios. But occasionally, between the lines of scientific papers and technical discussions, another emotion becomes visible. Concern. Not panic. Not sensationalism. Concern rooted in the realization that the Earth system may be entering conditions modern civilization has never directly experienced before. During events like this recent resonance wave, some researchers quietly ask questions they rarely phrase publicly in dramatic terms. What happens if synchronized atmospheric extremes become significantly more frequent? What happens if major agricultural regions fail simultaneously more often than historical systems were designed to tolerate? What happens if infrastructure adaptation moves slower than atmospheric destabilization? These are not fringe questions anymore. They are increasingly central to climate resilience research. And the reason scientists speak carefully is because the answers remain uncertain. The atmosphere is extraordinarily complex. Natural variability still exists. Some years remain relatively stable. Some regions may temporarily benefit from certain changes. But uncertainty cuts both ways. It means the future could be less severe than worst-case projections. It also means some risks may still be underestimated, especially risks involving compound events and atmospheric synchronization. During the 20th century, climate risk was often imagined as gradual warming distributed relatively evenly across time. But modern observations increasingly suggest the climate system may behave more episodically, uncritically than earlier public understanding assumed. Long quiet periods interrupted by sudden bursts of synchronized extremes. Persistent heat domes. Stored flood patterns. Multi-region agricultural stress. Simultaneous wildfire corridors. The atmosphere shifting rapidly from one amplified state to another. Scientists rarely describe these patterns emotionally because emotional language can distort scientific clarity. But behind closed doors, many researchers understand exactly how unusual these observations are becoming. The Earth system is not merely warming. It is reorganizing energy differently across oceans, atmosphere, ice, and land. And during resonance events, that reorganization becomes visible all at once. This does not mean civilization is doomed. Human societies remain adaptive, innovative, and resilient. But it does mean the future atmosphere may behave in ways historical experience alone can no longer reliably guide us through. And perhaps that is the deepest, unsettling truth hidden inside this entire story. Not that the atmosphere produced one extraordinary event, but that the atmosphere may be teaching us, slowly and repeatedly, that extraordinary events are becoming part of the new baseline of the modern world. Every civilization assumes the environment around it will remain within certain boundaries. Rivers will flood occasionally, but not endlessly. Heat waves will happen, but not in impossible seasons. Storms will intensify, but eventually move on. Modern society was built around the belief that the atmosphere fluctuates within a relatively stable, operating range. But what scientists are increasingly observing is not merely stronger weather. It is the atmosphere probing the outer edges of those historical boundaries more frequently than before. During this recent resonance event, multiple systems approached operational thresholds simultaneously. Heat levels neared the upper edge of climatological expectations for May. Fire weather conditions reached extreme classifications unusually early in the season. Flooding intensified beneath stalled rainfall corridors while mountain snow returned with winter-like severity. None of these events individually broke the planet, but together they revealed something profound. The atmosphere is capable of testing multiple societal limits at once, and civilization is not optimized for synchronized stress. Emergency management systems function best when disasters remain isolated. Power grids recover more easily when neighboring regions remain stable. Agricultural markets absorb shocks when crop failures stay regional. Insurance industries survive because most disasters historically remain statistically independent from one another. But atmospheric resonance changes that arithmetic. One stalled wave can create simultaneous pressure on food systems, transportation, energy demand, healthcare infrastructure, water management, and emergency response, all at once. Scientists increasingly warn that the danger of climate destabilization may emerge not through singular collapse, but through cumulative overlapping stress events repeated faster than systems can recover. The atmosphere does not need to become permanently catastrophic everywhere. It only needs to repeatedly push multiple systems near their limits simultaneously. And over time, the strain accumulates. Reservoirs decline. Insurance costs rise. Infrastructure ages under repeated extremes. Ecosystems lose resilience. Human adaptation budgets become exhausted. Quietly, gradually, civilization begins spending more energy simply maintaining stability against a more volatile atmosphere. This is why events like the recent wave pattern matter so much scientifically. They provide glimpses into how future climate risk may actually unfold, not as isolated disasters, but as synchronized stress distributed across entire continents at once. And overhead, invisible to nearly everyone below, the jet stream continues shaping those risks through planetary waves most people never even know exist. One of the greatest illusions modern civilization ever created is the idea that national borders divide environmental reality. On maps, countries appear separate and self-contained. But the atmosphere ignores every border humans have ever drawn. Air masses move freely across continents undaughted. Smoke from Canadian wildfires drifts into American cities. Saharan dust crosses the Atlantic and reaches the Caribbean. Heat domes expand across multiple nations simultaneously. Planetary waves wrap around the hemisphere itself. During this recent resonance event, the atmospheric structures stretched from the Pacific Northwest through the Rockies, across the plains, into the eastern United States, and outward into the Atlantic Ocean. The atmosphere behaved as one continuous system. And increasingly, climate researchers warn that many future risks must be understood at planetary scales rather than national scales. Food systems are global. Energy markets are global. Atmospheric circulation is global. Ocean warming is global. One region's drought influences another region's grain prices. One continent's wildfire smoke alters atmospheric chemistry elsewhere. Tropical ocean temperatures reshape rainfall thousands of miles away. The Earth system is deeply interconnected whether political systems recognize it or not. This becomes especially important during synchronized resonance events. A persistent wave over North America can alter downstream circulation into Europe days later. Changes in Arctic temperatures influence jet stream behavior across multiple continents simultaneously. ENSO conditions in the Pacific reshape storm tracks across the world. Climate is not a collection of local events. It is one giant fluid system continuously redistributing energy across the planet. Scientists studying atmospheric teleconnections have spent decades documenting these relationships. But only recently has the public begun experiencing their consequences directly through increasingly synchronized extremes. Heat waves no longer remain isolated regional curiosities. Wildfire smoke no longer stays near the fires that created it. Floods and droughts increasingly emerge within globally connected circulation patterns. The atmosphere is revealing its planetary nature more visibly than ever before. And perhaps this is one of the most important realizations humanity may need during the coming century. Climate adaptation cannot remain purely local while atmospheric dynamics remain global. The sky above every nation is physically connected to the sky above every other nation. And when planetary waves amplify, civilization experiences that connection whether it is prepared for it or not to. Somewhere tonight, high above the sleeping world, winds are already carrying the seeds of weather systems that will affect places thousands of miles away days from now's away days. The atmosphere has always been connected. Humanity is only beginning to realize how deeply. Every hour of every day, hundreds of satellites orbit silently above Earth, watching the atmosphere move. They track ocean temperatures, cloud formation, wildfire smoke, drought stress, sea ice decline, jet stream motion, soil moisture, atmospheric chemistry, and heat radiating from cities after sunset. Together, these satellites create one of the most detailed environmental monitoring systems humanity has ever built. And what they are revealing about the modern atmosphere is both extraordinary and deeply unsettling. From space, the Earth no longer looks climatically stable in the way it once did. Scientists can now observe planetary-scale heat anomalies spreading across oceans, smoke plumes stretching between continents, atmospheric rivers transporting enormous amounts of moisture across thousands of miles, and persistent blocking patterns remaining nearly stationary over regions for days or weeks at a time. The atmosphere appears increasingly energetic, increasingly synchronized, and increasingly capable of producing extremes simultaneously across multiple regions. During this recent resonance event, satellites captured the entire structure in real time, a massive ridge expanding over the eastern United States, a deep trough digging into the Rockies, severe storm clusters erupting across the plains, dry descending air intensifying fire danger farther south. From the ground, people experienced separate local disasters. From space, scientists watched one interconnected atmospheric engine operating across the continent. This perspective changes how researchers understand climate risk. The atmosphere is not simply warming evenly everywhere. It is reorganizing energy dynamically across the planet. Some regions become hotter and drier, others wetter and stormier. Some experience prolonged atmospheric stagnation while others endure rapid oscillations between extremes. And because satellites continuously compare modern observations against historical records, scientists can now detect shifts that earlier generations could only guess at. Ocean temperatures rising beyond previous benchmarks. Arctic sea ice retreating faster than expected. Wildfire seasons lengthening. Heat waves arriving earlier. Moisture transport becoming more intense. The planet is visibly changing from orbit. Yet perhaps the most remarkable part is how quietly these transformations occur from space. Earth still looks beautiful. Clouds still spiral across oceans elegantly. Sunlight still glows along coastlines at night. But hidden inside those patterns are subtle signals that the atmosphere modern civilization evolved under is gradually shifting into something new. And somewhere above the sleeping world tonight, satellites continue watching the atmosphere breathe, measuring every wave, every storm, every thermal anomaly, trying to understand how quickly the Earth system is changing and what kinds of skies humanity may inherit in the decades ahead. Scientists are not easily shocked by weather. Meteorologists spend their lives studying chaos. Climate researchers routinely analyze data spanning hurricanes, mega droughts, floods, heat waves, and volcanic winters across centuries of Earth history. They understand that the atmosphere has always contained extremes. But, over the last several years, something subtle has changed inside the scientific community itself. Researchers have become increasingly concerned not just about warming, but about the growing instability and synchronization of atmospheric behavior. This concern rarely appears dramatically in headlines because scientific culture rewards caution and evidence. But, inside conferences, peer-reviewed papers, and technical discussions, many scientists now openly acknowledge that some observed climate behaviors are evolving faster than expected. Marine heat waves intensify beyond modeled averages. Wildfire seasons overlap with severe drought more frequently. Atmospheric blocking patterns persist longer. Simultaneous crop stress emerges across multiple continents. The atmosphere appears increasingly willing to enter amplified states once considered rare. During this recent resonance event, scientists watching operational data recognized signatures they had been discussing in research literature for years. Slow-moving Rosby waves, persistent ridging, synchronized extremes, compound hazards, and atmospheric locking behavior. What disturbed many researchers was not simply the event itself, but how clearly it matched theoretical concerns about future climate amplification. The atmosphere was behaving exactly the way some studies suggested it eventually might. And perhaps most unsettling of all, these changes are still unfolding during relatively early stages of global warming compared to projections later this century. This is one reason many scientists increasingly emphasize adaptation alongside mitigation. Even if greenhouse gas emissions slow dramatically tomorrow, the oceans and atmosphere already contain enormous amounts of stored heat capable of influencing climate behavior for decades ahead. Some level of further disruption is already locked into the system. The challenge now becomes determining how societies adapt to increasing atmospheric volatility while simultaneously attempting to reduce future warming risks. But adaptation itself becomes difficult when the climate system changes faster than infrastructure and institutions can respond. Cities require decades to redesign. Agricultural systems evolve slowly. Water infrastructure is enormously expensive to rebuild. Political systems often react far slower than environmental systems change. And overhead, the atmosphere continues responding to physics regardless of human timelines. Quietly, many researchers now believe humanity is entering one of the most important environmental transitions in modern history. Not because the world will end suddenly, but because the atmosphere may increasingly behave in ways no civilization has previously experienced at global scale. And the people who understand the sky best are beginning to realize just how profound that transition may become. The atmosphere may be the most complex machine on Earth. Not built by humans, not controlled by governments, not governed by economics or ideology, but by physics operating across an entire planet. Every second, billions of interactions unfold simultaneously between sunlight, oceans, clouds, ice, forests, deserts, mountain ranges, and invisible gases circulating through the sky. Tiny changes in one region ripple outward through systems so interconnected that no human mind can fully visualize them all at once. And yet, despite its complexity, the atmosphere follows patterns, rhythms, feedback loops, balances built over thousands of years, which is why scientists became alarmed when those balances began shifting faster than expected. During this recent resonance event, the atmosphere behaved like a tightly linked global engine. Heat accumulated beneath the eastern ridge, while Arctic origin air plunged southward into the Rockies. Gulf moisture surged northward beneath unstable upper-level winds. Drought intensified fire danger in one region, while persistent rainfall generated flood risks in another. The atmosphere was redistributing energy across the continent with extraordinary efficiency. To most people, it looked chaotic, but scientifically, it was highly organized chaos driven by planetary-scale wave mechanics. Researchers increasingly believe one of the defining features of future climate behavior may be amplification of these connected systems. Not isolated anomalies, but chain reactions. Oceans warming faster influence evaporation rates. Evaporation alters atmospheric moisture content. Moisture changes storm intensity. Drought alters soil feedbacks. Soil feedbacks amplify heat waves. Heat waves intensify wildfire conditions. Wildfires inject smoke and aerosols back into the atmosphere. Everything interacts. The Earth system behaves less like separate components and more like one integrated living engine, continuously seeking balance. The frightening part is that human civilization evolved during an unusually stable climatic period known as the Holocene. Agriculture, cities, trade routes, infrastructure, and political systems all emerged under relatively predictable atmospheric behavior compared to much of Earth's deeper history. But now the climate system is absorbing more energy than it releases back into space. Oceans store the excess heat. Ice systems respond. Atmospheric circulation adjusts. Slowly at first, then more visibly, the machine begins operating differently. And perhaps this is why resonance events feel so psychologically disturbing. They reveal the scale of the system humans actually live inside. The atmosphere is not merely weather happening above civilization. Civilization exists inside the atmosphere, fully dependent on its stability, every hour of every day. Food production, transportation, freshwater, energy, health, economics, migration, and security all ultimately depend on the behavior of the sky. And during events like this, humanity briefly sees how interconnected everything truly is. Most disasters become dangerous because they overwhelm one system at a time. A hurricane damages a coastline. A drought stresses agriculture. A heatwave strains electrical demand. But atmospheric resonance events introduce another possibility entirely: cascading failures across multiple systems simultaneously. This is what increasingly concerns climate resilience researchers around the world. Modern civilization is highly efficient, but efficiency often reduces redundancy. Food systems depend on global transportation networks. Transportation depends on stable infrastructure and energy supplies. Energy systems depend on predictable temperature ranges and water availability. Healthcare systems depend on all of them functioning together. Under ordinary conditions, this interdependence creates remarkable stability. But under synchronized climate extremes, it can create vulnerability. During this recent atmospheric event, multiple stressors emerged at once across the United States. Heat increased electricity demand. Severe storms threatened transmission infrastructure. Flood risks disrupted transportation corridors. Wildfire conditions expanded across drought-stricken regions. Snow impacted mountain travel routes unusually late into spring. Individually, none of these effects collapsed the system. But together, they demonstrated how quickly compound stress can spread across modern infrastructure networks. Scientists studying systemic climate risk warn that future hazards may increasingly arrive not as isolated disasters, but as overlapping disruptions, interacting faster than recovery systems can respond. A prolonged heat wave increases electrical demand, while drought reduces hydropower capacity. Wildfire smoke worsens respiratory illness during hospital overcrowding. Flooding damages transportation during supply chain stress. Crop failures increase food costs during economic instability. The atmosphere does not create these vulnerabilities intentionally, but resonance patterns can expose how deeply interconnected modern civilization truly is. And perhaps most unsettling of all, cascading failures often begin subtly. Small disruptions accumulate quietly before larger systems finally destabilize. A stressed power grid here, an insurance withdrawal there, reservoir depletion elsewhere, agricultural losses increasing gradually over years, infrastructure maintenance delayed because adaptation costs rise faster than budgets can absorb. Civilization rarely collapses dramatically overnight. More often, systems slowly lose resilience until extreme events expose how fragile stability had already become underneath. This is why many climate scientists increasingly focus not only on preventing future warming, but on strengthening resilience against synchronized shocks already beginning to emerge. Because the atmosphere does not need to destroy civilization directly to reshape it profoundly. It only needs to repeatedly test the system civilization depends on until adaptation becomes unavoidable. And overhead, invisible planetary waves continue determining where those tests appear next. Human memory is short compared to the atmosphere. Civilizations remember decades. The climate system remembers centuries. Oceans remember heat long after headlands disappear. Forests remember drought through weakened roots and dry fuel accumulation. Ice sheets remember warming through slow, irreversible retreat. And because human societies tend to focus on immediate crises, it becomes difficult to recognize long-term environmental shifts while living inside them. This is one reason atmospheric change often feels surreal. People compare each new extreme only against recent memory, rather than against deep historical baselines. A dangerous heatwave becomes another hot summer. A once-in-a-generation flood becomes bad weather. Smoke-filled skies become seasonal inconvenience. But scientifically, the atmosphere is shifting far faster than collective memory can emotionally process. During this recent resonance event, meteorologists repeatedly described conditions approaching the edge of climatological expectations for May. Yet within days, public attention began moving elsewhere. The atmosphere reset temporarily. News cycles advanced. Life continued. This cycle of normalization may become one of the defining psychological characteristics of the 21st century. Humanity adapting emotionally to atmospheric conditions changing faster than cultural memory can fully register. Scientists studying risk perception warn that people naturally underestimate gradual systemic shifts because the human brain evolved to prioritize immediate, local threats rather than slow planetary transformations. But the atmosphere operates across scales much larger than human intuition. A warmer ocean today influences atmospheric circulation years later. Arctic warming reshapes jet stream behavior across decades. Soil moisture deficits accumulate season after season before amplifying major heatwaves. The climate system moves slowly until suddenly it does not. And during resonance events, the hidden acceleration becomes visible all at once. Entire continents experience synchronized extremes under one planetary wave pattern. This is why researchers increasingly emphasize historical context when discussing modern climate behavior. The Earth has always experienced variability. But the rate at which background conditions are now shifting is extraordinary within the timescale of modern civilization. Oceans warming, ice retreating, atmospheric moisture increasing, fire seasons expanding, heat arriving earlier. The atmosphere is evolving faster than the stories societies tell themselves about what normal weather should feel like. And somewhere inside that mismatch lies one of the greatest emotional challenges humanity may face ahead. Learning to recognize environmental transformation while still living inside the middle of it. What made this atmospheric event so scientifically important was not only its intensity, it was its structure. The wave revealed how climate risk may increasingly operate in the modern world, interconnected, synchronized, and amplified across multiple systems simultaneously. One stationary atmospheric configuration produced blizzards, heat waves, severe storms, flood risks, drought intensification, and wildfire danger all at once. Not sequentially, simultaneously. And that is the warning hidden inside the wave. Civilization is entering an era where the atmosphere may no longer deliver disasters one at a time. For decades, climate risk was often imagined as gradual warming, spread relatively evenly through the future. But modern observations increasingly suggest something more dynamic is unfolding. The atmosphere appears capable of organizing energy into powerful resonance patterns that redistribute extremes across enormous distances simultaneously. Heat builds beneath ridges. Flooding intensifies beneath stalled storm tracks. Fire weather expands under descending dry air. Agricultural stress spreads across multiple regions together. And because these events overlap, recovery becomes far more difficult than under isolated disasters. Scientists increasingly refer to this as compound climate risk, where the interaction between hazards becomes more dangerous than any single hazard alone. A heatwave during drought becomes more severe than heat alone. Wildfire smoke during urban heat emergencies worsens health impacts dramatically. Flooding during infrastructure strain creates cascading transportation failures. The atmosphere turns separate vulnerabilities into interconnected crises. During this recent event, the atmosphere briefly exposed that future in miniature. It showed how one planetary-scale wave could synchronize stress across a continent. And perhaps most unsettling of all, it did so before peak summer energy had even arrived. The oceans are still warming. Soil moisture deficits are still developing. The northern hemisphere has not yet reached its maximum seasonal heating, which means the atmosphere may still be capable of entering even stronger resonance states later in the season or in future decades. This does not guarantee constant catastrophe. Natural variability still exists. Stable years will still occur. Quiet seasons will still happen. But the probability distribution beneath the atmosphere appears to be changing. The sky is entering highly amplified states more often than modern civilization evolved expecting. And somewhere tonight, inside forecasting centers glowing with radar loops and satellite imagery. Scientists are watching the next wave beginning to organize over the Pacific Ocean, wondering whether the atmosphere is preparing to test those limits once again. For thousands of years, humanity looked at the sky as something eternal. Storms came and went, seasons shifted, winters arrived, summers followed, but the atmosphere itself felt permanent, stable, reliable. The background system beneath civilization. Farmers planted according to it. Cities expanded beneath it. Entire cultures organized their calendars, economies, and rituals around predictable seasonal cycles. But something has changed in the modern age. For the first time in human history, civilization is beginning to realize that the atmosphere itself can evolve within a single lifetime. Not over geological ages. Not over ancient epochs. Within decades. People alive today have watched fire seasons lengthen, heat waves intensify, glaciers retreat, oceans warm, and weather records repeatedly fall. They have watched once rare extremes become increasingly familiar. And perhaps most psychologically unsettling of all, they have begun feeling uncertainty about the sky itself. During this recent resonance event, that uncertainty became visible across the continent. Forecast maps looked surreal. Heat spread into regions weeks ahead of seasonal expectation. Blizzard conditions erupted while summer-like temperatures developed elsewhere. Severe storms intensified beneath atmospheric structures that barely moved. The atmosphere no longer felt fully predictable in the way previous generations assumed it would remain. Scientists increasingly describe this transition as the emergence of climate non-state inertia. In simple terms, the past is becoming less reliable as a guide to the future. Historical averages no longer guarantee future stability because the baseline conditions underneath the atmosphere are shifting continuously. Oceans are warmer. Arctic systems are changing. Soil moisture patterns are evolving. The jet stream behaves differently under altered temperature gradient. And as these background conditions change, atmospheric behavior changes with them. Civilization is entering a world where historical climate memory may no longer fully apply. This realization carries enormous consequences. Infrastructure engineering depends on historical probabilities. Agricultural planning depends on seasonal consistency. Insurance systems depend on expected recurrence intervals. Water management depends on predictable snowpack and rainfall timing. But non-stationary climates destabilize those assumptions because yesterday's extremes no longer define tomorrow's limits. And overhead, the atmosphere continues responding to physics, not to human expectations. The frightening truth hidden inside this entire story is not simply that one extraordinary atmospheric event occurred. It is that the atmosphere may continue evolving into states modern civilization has no historical experience managing at planetary scale. And somewhere tonight, millions of people are falling asleep beneath skies that no longer behave exactly like the skies humanity built civilization beneath. There is one question hiding underneath every climate discussion, every atmospheric model, every satellite observation, and every forecast map glowing inside research centers late at night. How far can this system go? Scientists can estimate probabilities. They can simulate warming scenarios. They can model circulation patterns on ocean heat uptake. But the Earth system remains extraordinarily complex, filled with feedback loops, thresholds, and interactions humanity is still trying to fully understand. This uncertainty is not ignorant. It is the nature of planetary systems operating across enormous scales. During this recent resonance event, the atmosphere demonstrated behavior many researchers had warned about theoretically for years. Synchronized extremes connected through amplified planetary waves. Heat, snow, flooding, severe storms, and fire weather all linked beneath one stalled circulation pattern. The atmosphere revealed how interconnected modern climate hazards can become. But the larger question remains unanswered. Was this merely an unusual event within natural variability enhanced by warming? Or was it part of a deeper transition toward more frequent atmospheric resonance in the decades ahead? Scientists do not fully know yet. Some observational trends strongly suggest booking patterns and synchronized extremes are increasing. Other uncertainties remain debated. The climate system is still evolving in real time, but one reality is becoming increasingly difficult to ignore. The atmosphere now contains more energy than it did during the centuries when modern civilization developed. Warmer oceans evaporate more moisture. Hotter air intensifies drought stress. Altered Arctic temperature gradients influence upper-level circulation. Every component interacts with every other component, which means future atmospheric behavior may not simply become warmer. It may become more volatile, more amplified, and more synchronized. And this uncertainty itself may be one of the greatest challenges humanity faces. Civilization prefers predictable risks. Economies function best when probabilities remain stable. Infrastructure planning depends on knowing what conditions are likely. But the atmosphere appears increasingly willing to explore states near the edge of historical experience. The sky is becoming less familiar. And perhaps the most haunting part of all is this: future generations may look back on events like this recent wave pattern not as rare anomalies, but as early signals humanity failed to fully understand while they were still emerging. Somewhere high above the Earth tonight, the jet stream continues moving through darkness, carrying invisible waves around the hemisphere. And hidden inside those waves may already be the shape of the climate future, still waiting to arrive. There is a moment late at night, usually sometime after midnight, when the atmosphere becomes strangely quiet. Roads empty. City is dim. Temperatures slowly fall beneath darkened skies. Most people are asleep, unaware that above them the entire planet remains in motion. Jet streams continue circling the hemisphere. Oceans continue releasing stored heat into the air. Invisible rivers of moisture continue moving between continents. The atmosphere never truly rests. And perhaps that is the deepest realization hidden inside the story. The climate system is alive with movement every second of every day, constantly redistributing energy across Earth whether humanity notices or notices. During this recent resonance event, millions experienced the consequences of that movement directly. Heat trapped beneath stalled ridges. Floodwaters rising beneath repeated storms. Fire danger expanding across drought-stricken landscapes. Blizzards erupting where spring should already have taken hold. But tonight, after the headlines fade and the warnings expire, the atmosphere continues evolving above the sleeping world. Scientists know that no single event defines the future entirely. The Earth system still contains uncertainty, resilience, and natural variability. Yet at the same time, researchers also know something fundamental has changed. The atmosphere modern civilization inherited is no longer operating exactly the way it once did. It accumulates more easily. Moisture transport becomes more intense. Ocean temperatures continue rising. Atmospheric patterns increasingly drift toward amplified states. And because these changes interact together, the climate system can now produce combinations of extremes that feel emotionally unreal, even while remaining physically explainable. This is why atmospheric resonance events disturb scientists so deeply. They expose how connected everything truly is. One planetary wave reshapes conditions across an entire continent. One stalled jet stream pattern synchronizes disasters across thousands of miles simultaneously. The atmosphere reveals itself not as separate local forecasts, but as one continuous global engine. And somewhere tonight, while satellites watch from orbit and researchers monitor model simulations glowing across computer screens, another wave is already forming. Another ridge beginning to amplify. Another trough starting to deepen. The atmosphere keeps moving forward, whether humanity fully understands it or not. Perhaps that is what makes the sky feel different now. Not because it has become evil or conscious or hostile, but because humanity has finally begun noticing how immense and powerful the system above us has always been. Civilization exists inside an ocean of air controlled by planetary physics far larger than any nation, economy, or generation. And during rare moments like this, the atmosphere briefly reminds humanity that it is still the dominant force shaping life on Earth. Someday, decades from now, Another generation will look back at this era and try to understand what it felt like to live during the beginning of atmospheric transformation. They will study the heat waves, the wildfire seasons, the strange winters, the stalled floods, the synchronized disasters, and the growing scientific realization that the climate system itself was entering a new phase. They may wonder whether people fully understood what was happening while it unfolded around them. The truth is complicated. Humanity understands more about the atmosphere today than at any other moment in history. Satellites observe the entire planet continuously. Climate models simulate global circulation in astonishing detail. Scientists track ocean heat content, jet stream behavior, ice sheet loss, atmospheric chemistry, and planetary energy imbalance with extraordinary precision. And yet, despite all that knowledge, there remains something emotionally difficult about accepting that the sky itself can change within the span of a civilization. Because the atmosphere feels permanent. It always has. It surrounds every human life from birth to death. Entire histories unfolded beneath seemingly stable seasons. But now the Earth's system is shifting faster than historical memory can comfortably absorb. Oceans are warming. Ice is retreating. The jet stream behaves differently. Resonance events emerge more often. The atmosphere carries more heat, more moisture imbalance, and more potential energy than the generations before us ever experienced. During this recent event, the atmosphere offered a glimpse of what the future may look like. One planetary wave synchronizing extremes across an entire continent. Heat, snow, storms, floods, and fire all unfolding together beneath one interconnected system. Not isolated disasters. One atmospheric machine redistributing energy across the planet in real time. And perhaps this is the final lesson hidden inside the sky above us tonight. Humanity is not separate from the atmosphere. Civilization is not outside nature observing climate safely from a distance. Every city, every harvest, every power grid, every road, every nation exists entirely within the thin layer of air surrounding this planet. The atmosphere is the foundation beneath modern civilization itself. And now that foundation is beginning to shift. Yet even in that uncertainty, there is still something extraordinary about this moment in human history. Humanity is becoming aware of the planet as one interconnected system for the first time at global scale. The same satellites watching storms also reveal the beauty of Earth in breathtaking detail. The same science warning about climate risk also gives civilization the ability to adapt, prepare, and understand. Perhaps future generations will inherit a world more volatile than the one previous civilizations knew. But they may also inherit a deeper understanding of the atmosphere than any humans before them ever possessed. Tonight, somewhere above the dark oceans and sleeping cities of Earth, invisible planetary waves continue moving through the sky. The atmosphere breathes. The oceans store heat. The jet stream bends around the hemisphere. And beneath it all, humanity waits, watching the clouds, studying the data, trying to understand what kind of world is beginning to emerge above our heads before the story of this century is fully written.